Greetings, fellow seekers of knowledge. Welcome back to All You Could Know. Today, we're setting sail on a thrilling expedition into the realm of motion, guided by none other than Sir Isaac Newton himself. And no, we're not talking about the apple falling from the tree story, but rather his legendary laws of motion. 3 simple yet profound laws that govern how objects move in our universe. From the stillness of a rock to the sprint of a cheetah, from the flight of an airplane to the orbits of planets, all are choreographed by these laws. So whether you're a curious learner, an aspiring scientist, or simply a lover of knowledge, this journey promises to be an enlightening one. So buckle up as we delve into the heart of motion, inertia, force, and reaction. Strap in, because we're about to delve deep into the principles that orchestrate the dance of the cosmos. Let's initiate our exploration with Newton's first law, the law of inertia. This law is a foundation stone of physics, a principle that governs the world around us. It states that an object at rest will stay at rest, and an object in motion will stay in motion unless acted upon by an external force. Quite a mouthful, isn't it? But don't worry, we'll break it down together. Picture a soccer ball on a field. It's static, motionless at rest. Why? Because no external force has been applied to it. But what happens when a player kicks the ball? The ball moves, it's now in motion. That's Newton's first law in action. But there's more. The law also states that the ball will continue moving in the direction it was kicked, maintaining its speed or velocity, unless another external force interferes. This could be another player stopping the ball, or even the friction of the grass gradually slowing it down. Now, let's swap the soccer field for a frozen lake and imagine an ice skater gliding along. The ice provides very little friction, so when the skater pushes off, they'll continue to glide smoothly across the ice until they slow down or stop themselves. That's inertia in motion. The skater remains in motion until an external force, like friction or a deliberate stop, changes their state. Inertia, then, is the property of an object that resists changes in its state of motion. It's why you lurch forward when the car you're in suddenly stops, or why you're pushed back into your seat when the car accelerates. Your body, in its love of inertia, wants to keep doing what it's doing, staying still or moving until something else makes it do otherwise. So the next time you're in a moving car, or see a soccer ball whizzing past, remember Newton's first law, the law of inertia. It's not just a principle in a dusty old textbook, but a living, breathing law that's in constant play around us, revealing the hidden poetry of inertia. Now let's shift our focus to Newton's second law, a formula that may seem intimidating at first glance. Force equals mass times acceleration. That's right, my friends, it's as simple as F equals m times a. But what does this really mean? Let's break it down. Force is the push or pull that acts upon an object. Mass refers to the amount of matter in an object, and acceleration is the rate at which the object changes its velocity. So when we say force equals mass times acceleration, we're describing the relationship between these 3 variables. Think of it like this. If you've ever pushed a heavy shopping cart, you know it takes more effort to start it moving than to keep it moving. That's because the mass of the cart resists acceleration, requiring a greater force to change its speed or direction. This is Newton's second law in action. Now, let's take it a step further. What happens if the mass remains constant, but the force increases? The object accelerates, right? It's like pushing a swing. The harder you push, the faster the swing moves. And if you stop pushing, the swing slows down, thanks to our old friend, the force of gravity. But what if the force remains constant and the mass changes? Let's say you're pushing 2 shopping carts, one empty and one full. The full cart has more mass, so it accelerates slower than the empty one, even though the force you're applying is the same. So you see, Newton's second law isn't just a string of letters and numbers. It's a dynamic equation that illustrates the interplay of force, mass, and acceleration. It governs everything from the tiniest particles to the mightiest galaxies, from the way a ball rolls down a hill to how rockets blast off into space. And that, dear friends, is the beauty of Newton's second law. It's more than just a law of physics, it's a fundamental principle that shapes our understanding of the universe, turning complex physics into a captivating journey. Brace yourselves for the powerhouse Newton's third law, the law of action and reaction. This principle is a cornerstone of the universe's grand ballet, a dance of forces in perfect equilibrium. Newton's third law states, for every action, there's an equal and opposite reaction. This might sound like a tongue twister, but let's break it down with some real-world examples. Think about a rocket launching into space. As the rocket's engines ignite, a powerful thrust of gases spews out from the back. This forceful expulsion is the action. But what's the reaction? Well, the gases pushing against the rocket propel it upwards, hurtling it into the cosmos. The force of the gases downward equals the force of the rocket upward. Action and reaction perfectly balanced. But this law isn't limited to rocket science. It's present in our everyday lives. Let's consider a simple act of walking. When we walk, we push our foot backward against the ground. This is the action. And in turn, the ground pushes us forward. That's the reaction. Even in this mundane act, we can see Newton's third law at play. Every step we take is a dance of opposing forces. How about the recoil of a gun when it's fired? The bullet being propelled forward is the action, and the backward kick against your shoulder, that's the reaction. Again, action and reaction, equal and opposite. And it doesn't stop there. From the way birds flap their wings to take flight, to how a swimmer pushes water backwards to move forward, Newton's third law is a universal principle, governing the intricacies of movement in our world and beyond. So, the next time you see a rocket launch or simply take a walk, remember the cosmic equilibrium at play. Newton's third law, the law of action and reaction, is the invisible choreographer, orchestrating the dance of the cosmos where each step is a dance of opposing forces. Now let's take a hands-on approach with some exciting experiments to bring Newton's laws to life. Delving into the realm of practical demonstrations, we're going to make the seemingly abstract world of Newton's laws a tangible reality. Picture this, a miniature rocket launch. We're not just talking about a fun experiment, but a lively embodiment of Newton's third law. The rocket's thrust downwards forces it upwards, giving us a thrilling spectacle of action and reaction at work. Then consider a simple game of pool. The balls colliding on the table, that's Newton's first law in action. The stationary balls stay at rest until the cue ball. Our external force sends them scattering. The more force we apply, the more they accelerate, providing a dynamic illustration of Newton's second law. Ever wondered why you lurch forward when a car suddenly stops? That's your body demonstrating the law of inertia, Newton's first law. Your body in motion wants to continue in motion, even when the car has other plans. And let's not forget the classic demonstration of a pendulum swing. A ball suspended from a string swings back and forth, each swing a testament to the forces at play. The pendulum's motion is a dance between inertia, force, and reaction, a beautiful symphony of Newton's laws in harmony. But we're not just here to observe. These experiments are your playground. Through them, you can touch, feel, and see the laws that govern the universe. You'll discover that every push, pull, twist, or turn you make is a fascinating interaction with the fundamental principles of motion. So, as we launch rockets, collide pool balls, halt cars, and swing pendulums, we're not just having fun with science. We're experiencing the laws that shape our world and the cosmos beyond. We're turning the invisible forces that guide our universe into something we can see, touch, and understand. And by bringing these laws to life, we're turning our theoretical understanding into a visual spectacle. There you have it, an in-depth exploration of Newton's laws of motion. We've journeyed through the law of inertia, seen how force and acceleration intertwine, and balanced on the tightrope of action and reaction. These aren't mere abstract principles confined to the pages of a physics textbook. They're the invisible puppeteers guiding the dance of all things in motion. From the stillness of a parked car to the thrust of a rocket launching into space, Newton's laws are at play. They allow the pendulum to sway and the planets to maintain their celestial waltz. They're the unseen directors of the cosmic theater, the script that dictates the ebb and flow of movement in our universe. So the next time you witness the majesty of a soaring bird or marvel at the stars' steady march across the night sky, remember Newton's laws. Until our next scientific rendezvous, keep exploring the wonders of motion and the laws that govern our reality.